next example problem, we have an object that's attached to a spring. Initially, the spring is stretched a distance of 4 centimeters beyond its natural length, but sometime later, that spring is stretched only a distance of 1 centimeter beyond its natural or unstretched length. And we're asked to find what is the work done on the object by the spring. Before proceeding with this problem, let's ask a question. Do we expect the work done on the object by the spring to be a positive number or a negative number? And what's our justification for that answer? We expect the work done on the object by the spring to be a positive number. How can we reason or justify that claim? Let's think of it this way. Let's suppose initially the spring is unstretched. So here's just the natural length of the spring. And then what do I have to do to actually stretch the spring? Well, to actually stretch the spring, I need to pull on it. So I apply a force and I will pull until the strength of my force pulling the object to the right is equal to the spring force when the spring is stretched 4 centimeters beyond its natural length. So at this point, the force of my pull and the force of the spring balance, and the net force on the object is 0. So now the object is just going to be stationary, it's not going to be moving. But then I will let go. When I let go, I am removing my force. If I remove my force, the only force acting on this mass is going to be the spring force. Because there is only one force acting on this mass, the mass will accelerate to the left. The object is going to go from not moving to moving with some speed. In other words, the object will gain kinetic energy as it accelerates to the left. When the spring force was the only force acting on the object, the spring force caused the object to gain kinetic energy. I could interpret that as saying the spring force did positive work on the object in this scenario. Similarly, we expect the spring force to do positive work when the object goes from being attached to a spring stretched 4 centimeters beyond its natural length to having the spring be stretched only 1 centimeter beyond its natural length. Whenever we work with problems in this course, we always want to work in units of kilograms and meters and seconds. I will typically write spring constants in terms of newtons per meter on exams, but in the homework, it is somewhat common to see the spring constant written as newtons per centimeter. So I'm going to convert the spring constant to newtons per meter. And to do that, I could write the spring constant is equal to 110 newtons per centimeter. And then I will multiply that by 100 centimeter over 1 meter. And when I do that, the centimeters cancel. And I get the spring constant is going to be 11,000 newtons per meter. Now this sounds like a really large number. 11,000 is big. 11,000 newtons is a really strong force. But remember, you're trying to take a spring and stretch it a distance of 1 meter. This is a really long distance to stretch a spring. So how could we find the work done on the object by the spring? One thought initially might be, what about trying work is FD cosine theta? We cannot use this equation. The reason we cannot use this is because this equation assumes that the force F is a constant force. But the spring force is given as negative kx, where x is the displacement or stretch of the spring. And as the displacement of the spring changes, the spring force is going to change. And so this force is not going to be a constant force, and we cannot use this. What about trying the work kinetic energy theorem? W net equals delta KE. You could imagine maybe using this, but it's not immediately obvious what the kinetic energies are going to be. So instead of these, let's try something from the previous lecture slide videos. We learned in the previous video that the total work done by all the conservative forces acting on an object, W net conservative, could be written as negative change in potential energy. Here, the only conservative force that is important for this problem will be the spring force. So the spring force is going to be this entire term. So I could write the total work done by the spring force is going to be negative 1/2 k x final square minus 1/2 k x initial square. I know what the spring constant is. I know x final and x initial. They were given as 4 centimeter and 1 centimeter respectively. So I have enough information to plug numbers in everywhere and find the work done by the spring. So I could write the work done by the spring is equal to negative 1/2 times 11,000. X final is 1 centimeter. I write that as 0.01 square minus 1/2 11,000. X initial square was 4 centimeters, 0.04 squared. And when I put this entire term in a calculator, I find the work done by the spring is 8.25 joules. So as we expected, we got a positive number for the work done on the object by the spring. We said previously that for every conservative force, there is a potential energy associated with that force. We said gravity and the spring force are examples of conservative forces, and we have a notion of gravitational potential energy and spring potential energy. If I tell you right now that the Coulomb force is a conservative force, even though we did not yet learn about the Coulomb force and we don't know how to write the equation that describes the Coulomb force, right away you know there will be a potential energy associated with the Coulomb force. So what is the actual relationship between a potential energy and a conservative force? To address that question, let's first remember what potential energy is. We said that potential energy is a form of energy associated with the configuration of objects in a system. In other words, potential energy is an energy of position. Potential energy could therefore be written as a function of position, or x, y, and z. So I imagine that I have an x and y axis. You could pretend that the z axis is coming out of the board. And if I have an object that has a location, and then that object may move to a new location, that object could have a notion of an initial position and a final position, and we could meaningfully talk about a change in that object's potential energy. As a more specific example, here I'm being completely general. I want the potential energy to be a function of position in as arbitrary a way as possible. Let's think about the gravitational potential energy. We said the gravitational potential energy could be written as mgy. Energy itself is a scalar quantity, and this is a scalar function that depends on position. The information that encodes the position is contained in this term y, basically y being my height above the ground. In this potential energy due to gravity equation, we generally assume that the mass and the acceleration due to gravity are going to be constant throughout this problem. So what is the actual relationship between a conservative force and the potential energy associated with that force? Now, for full disclosure, the actual relationship is a calculus-based relationship. Physics 121 is an algebra-based course, so you will not need to actually perform any derivatives or integrals in this course, but I want to mention it for completeness. The relationship between a conservative force and a potential energy associated with that force could be written as that force is equal to negative nabla PE. So here we have our force, here we have potential energy, a negative sign, and then we have this upside down triangle that has a vector arrow above it. This upside down triangle is known as the Nabla operator. It is not a function, it is not a number, it is an operator. So in math, what is an operator? Think about a derivative. A derivative is not a number, a derivative is not a function, but a derivative is something that you apply to functions and do to those functions. So if I were to write the derivative of x, okay, this isn't anything on its own. It needs to be acting on something. So I could talk about the derivative of a function, f of x, and now I have a meaningful statement. So I think of this d dx as an operator. It will do something to this function. Nabla could be thought of as a derivative that was promoted to a vector. So Nabla is kind of like a derivative with directions associated with it. So the force itself is a vector. A force is a type of object that has three components. We have a notion of the x component of the force, we have a notion of the y component of the force, and we have a notion of the z component of a force. Now, the Nabla operator is kind of like a derivative that got promoted to a vector. So I would write the x component of the force is negative d dx pe, and here I'm taking partial derivatives. The y component of the force could be written as negative d dy pe, and the z component of the force could be written as negative d dz pe. So I take the derivative with respect to x of the potential energy to get the x component of the force. I take the derivative with respect to y of the potential energy to get the y component of the force. I take the derivative of the potential energy with respect to z, and I get the z component of the force. And this is three equations written right here, but I could condense them all into one equation by writing it in this form over here. As a specific example of this, let's consider the force of gravity and the potential energy due to gravity. If we think about an object that is right here, we know that this object will feel a downward force of gravity. So I could draw the force of gravity vector to look something like this. If I were to write this force of gravity vector in its components, I would write the force of gravity in the x direction is going to be 0. The force of gravity in the y direction will be negative mg, and the force of gravity in the z direction will be 0 again. We said horizontally to the right is the x direction, horizontally out of the board is the z direction, and vertically upward is the y direction. Therefore, I expect the force of gravity to be negative mg in the y direction and 0 in the other two directions. Is this what we find if we plug this potential energy due to gravity in over here? So let's try that out. So the potential energy due to gravity is mgy. I could write that there, and there. Now, when I take a partial derivative with respect to x, this partial derivative is looking for x. And every term other than x, this partial derivative will assume is a constant. This partial derivative does not see any x's in here, so this partial derivative thinks it's taking a derivative of just a constant, and the derivative of a constant is 0. Now, when I take the partial derivative of this term with respect to y, it does see a y right over here. M and g are constant, and the derivative of y with respect to y is just going to be 1. So I would get negative mg here. And the partial derivative with respect to z, there are no z's in this term in parentheses. So the partial derivative treats everything inside the parentheses as a constant, so I get 0 again. As I mentioned previously, this is an algebra-based physics course. You do not need to do any calculus. You don't need to take any integrals or perform any derivatives in this course for any homework or exam. However, I did tell you that there is a relationship between a conservative force and a potential energy associated with that force, and I did want to demonstrate what that is. But again, as I said, you will not need to actually perform any calculation similar to what we did here for Physics 121.